So my name is Jefferson Cooper, and I'll be discussing using a new inference model basically based on the embedding as opposed to the words themselves in order to hopefully have constant time inference that'll be faster and cheaper than what currently exists for text inference for language models. And just to briefly, you're all familiar, but just to briefly review what an embedding is real quick, it takes a word or a sentence or a paragraph, a text sequence of any length, and it converts it to a point in high dimensional space. And that point in high dimensional space is the important thing here. As a comparison, I'm trying to imagine language as having vector fields. In this example here, if you imagine space, if you look at this, if you put say a ball, for example, to the left of the planet Earth, it's going to drift to the right in order to then go into the Earth. If you put it slightly to the right of the Earth, it's going to go to the left. Basically, we have these explicit equations, gravity, in order to predict where any object is going to go based on its current position in space. We have this for physics, and the idea is that it would be very convenient if something like this existed for words in embedding space. And here's kind of an illustration of how that would work in a similar way to how the arrows were pointing to where an object might go here. You can see here that despite the phrase II exists in embedding space, but you're very rarely going to get there just because it's just not a sequence that you see popping up much in normal English. So you can almost imagine that there's some force repelling, you could say, the dialogue away from that, or some force dragging it towards more common continuations of the word I, like I want or I am. And so the idea is to use a neural network or a feed-forward network to approximate this type of function that's taking an embedding and changing it as you continue to add tokens to it. And the reason I would want to do this is because this changes the problem of text inference from, okay, here's all the previous words, and now I need to look at the relationship that all of them have to each other, to something simple like, here's the current point in space. Just from that, where will it be next? And can I reliably predict that? So some potential positive outcomes of this would be reduced inference time and reduced inference expenses. This would be constant time and constant compute in terms of inference, because again, each of these embeddings is a point in the same high dimensional space. So regardless of whether it's a sequence of, say, 10 words or 200 words, it's still the total same amount of computation that you have to do on the input. And both of these things will also lead to, hopefully, edge inference. Currently, a lot of language models are incredibly powerful, but many of them are too large to be able to fit or run comfortably on something like an iPhone, for example. So a lot of applications right now rely on APIs and models being hosted remotely with a lot of compute. And this could ideally open the way for edge inference and also just quicker and cheaper inference for all applications. Just as an illustration of how this works, basically you take the input prompt, because first it's still going to be text inference to begin with, and you turn it into an embedding. And from there, you feed this into the feed-forward network in order to predict what the next token would be. Not the next token, but what the entire phrase's embedding would be in space once you added another token. And then from there, you can feed that in as input again to predict, what would be the embedding of this text after 2 tokens, after 4 tokens, after 8 tokens? Once you've done this enough, you can actually turn an embedding back into the text that us humans read by using something known as vec2text. This was released recently, and it's also very critical to know for business because it is possible to convert embeddings back to text. And this is very important to know because if you have a vector database of, say, embeddings of customer data and you're sharing that with a third party, you just know that it's recoverable, and that's important. And vec2text is an illustration of this. The way that it works is it takes an embedding, again, in this high-dimensional embedding space, and it predicts based on that what the actual full sequence would be. And from there, it actually re-embeds its prediction and compares it to the ground truth embedding that was the input. And from there, it can self-correct repeatedly until it recovers almost all of or the entire input. So just note that it is possible to recover text from embeddings from a security perspective, and that's what I'm using here at the end to finally convert the embedding back into the response that a human would read. The training process for this network, I generated for this, I used GPT 3.5, and I just had to generate stories. I figured it would still be It's a narrower space, which would be more helpful for learning, but still a lot of variety in there. And whenever there was a story, I would basically take an input. For example, say the story started with I. So you take the embedding of I, what comes next? The embedding of I want. And so input, output. And then you can also do, here's the input, the embedding of I want, what came after that? I want to. And I use this as the training data so that way, from any embedding, predict where it would be if you added one more token to it in the embedding space. And I actually didn't end up using Bayesian neural networks. I think these would be awesome to use because they deal with probability. And again, if you start with one word, there's a chance that you can end up on multiple different words. It's not entirely deterministic. I just didn't get to that here, but I think it would be an excellent application. And that's the probability. In terms of the results, I scored it basically after 10 tokens. The prompt I gave it was, okay, generate a story and start it with the word it. And now after 10 tokens, I have an example of things that say GPT 3.5 would generate and the positions in embedding space. When I query my model, I basically take its strongest, I take its output after that and I compare it to its closest counterpart that GPT 3.5 generated. Because there could be valid answers that are far separate in embedding space. So I just want to see how close it is to what a normal network would generate. And I used baselines for this of GPT 3.5, which was the same thing I used to generate the training data, and also GPT-2. And I don't have the graphs here, but in terms of the score, GPT 3.5 would average around 12 in terms of its distance, or 0.12, I multiplied by 100, in terms of its distance from the cluster that I made for comparison, and GPT-2 would average about 60. 60 is about where you are when you have coherent text, but it's not really related to the tone or the message that a lot of the stories that the OpenAI GPT 3.5 was generating. When I did this with my model, again, I'm sorry, I don't have the visuals here, but it averaged about 30. So not necessarily as great as the training data that it was trained on so far, but significantly better than text that is entirely unrelated to the stories that GPT 3.5 tended to generate. And one interesting thing here is that when I was doing my test with this, actually the smaller networks tended to perform better. If I gave it the same amount of training, they would be more capable of keeping relevant information close to what a typical story would look like compared to larger networks, where they would kind of go crazy in the embedding space after a bit. This may be because of too little training data or too little training time, but it's still an important thing to note. I didn't compare with Bayesian networks, but I did see that feed-forward neural networks did perform better than networks with dropout. Networks with dropout, you get rid of some of the weights during the training process, and I thought that this would be helpful because it adds a little bit of probability and uncertainty to the predictions, and there should be uncertainty when predicting the next word in text, but that didn't seem to be the case. Feed-forward networks generally performed better, the smaller ones in particular. And in this graph showing relative performances, it would show that when you're looking at the baseline, in the graph showing relative performances, these networks averaged around 30 in terms of their distance from this cluster. Whereas again, GPT-2, that's more of just a generic text completion thing, so it wasn't really suited for this, was more 60. It was still plausible text, but not great. And the actual baseline, which would be the thing I used to generate the data to begin with, was still at 12. So this was a significant improvement off of just a normal network used on this, but still worse than the actual network I was drawing the stories from. In terms of shortcomings and next steps, while the inference can happen in constant time and these predictions can happen in constant time, the actual act of embedding the input text into the embedding space and then turning the vector back into text, that still happens using transformers. So that isn't fundamentally faster than what currently exists today. So the beginning and end steps of the process are not quicker. And model performance could stand to improve if I increased in size. I leave that as an exercise to people with better hardware than me because I can only fit so large of a model on my laptop. And model performance could also improve if I gave it more data. Again, if you have more compute, that would be easier to do. And there's no clear indicator of when to stop running networks. That's one big thing. When you're using a transformer, it can have end tokens. Because I'm operating in embedding space, it's kind of hard to tell when a paragraph ends just because it's just another point in space. Finally, I'd like a better way of evaluating loss for these networks. Again, I just generated examples and compared how it was relative to the closest example. That was just something I came up with. There could definitely be a more rigorous way of evaluating the efficacy of these. And I would also like to see, maybe it gets worse with every prediction it does. So maybe if I skip tokens, like maybe if I said, okay, predict what the text will be in 4 tokens as opposed to every single token, it would maintain accuracy for longer. Because in the graphs, you would see that the accuracy kind of falls off almost exponentially as you increase the number of tokens from the ground, from the initial prompt. And finally, I think that I could also reduce the number of embedding dimensions. I used ADA for this because vector text works on that, but that's an embedding format, by the way. And so instead of that, or off of that, I could also use, PCA, which is primary components analysis. I could get the most important dimensions of that. So maybe only 200 dimensions of this 1,500 dimension embedding space are actually meaningful for the most of the text content. And that might be easier for my model to understand too. Just having fewer inputs to take in, fewer outputs to predict. So that's one thing I would like to look into further as well. And so that's my presentation, and I'll be glad to take any questions. Thank you.